Right now, as you watch this video, there is another version of you watching something else entirely. Another version who said yes when you said no, who took the job you turned down, who married someone different, who made every single choice you didn't, and is living a completely different life because of it. And here's the part that should genuinely unsettle you. That other version of you might be just as real as you are. Welcome to the multiverse. For most of human history, this idea lived exclusively in the realm of science fiction. Parallel universes, alternate timelines, doors between realities. The stuff of comic books and blockbuster films. But something changed in the last few decades. Physicists, serious, rigorous, mathematically minded people, started looking at their equations and finding something they didn't expect. The multiverse wasn't just a fun idea. It was something the math kept pointing to, again and again, from completely different directions. Today, the multiverse is one of the most debated topics in theoretical physics. Not because it's flashy or cinematic, though it absolutely is, but because multiple independent lines of scientific reasoning keep arriving at the same conclusion. Our universe may not be the only one. Not even close. In this video, we're going to go through all of it. We'll start with what the multiverse actually is, and why it's not just one idea but several very different theories that all carry the same name. We'll dig into the quantum physics that suggests every decision you make might be splitting reality in two. We'll talk about you, specifically about the versions of you that might exist in other universes right now, living lives you can barely imagine. We'll look at the actual scientific evidence that hints at something beyond our cosmic horizon. We'll wrestle with the hardest question in this field. Can we ever prove any of this? And at the end, we'll sit with the implications, because if the multiverse is real, it changes everything. What free will means, what death means, what you mean. Let's go. Let's get one thing straight immediately. The multiverse is not one theory. It's a family of theories, different ideas that come from different areas of physics and mathematics, that all point toward the same general conclusion. There is more than one universe. The word universe used to mean everything. The totality of existence, the whole show. But the multiverse hypothesis forces us to redefine our terms. What we call the universe might be more precisely called the observable universe. The bubble of space we can see, limited by the distance light, has had time to travel since the Big Bang. About 93 billion light-years across. Incomprehensibly vast. But that doesn't mean it's all there is. In fact, according to several serious physical theories, our observable universe might be one tiny region in a much larger, possibly infinite, expanse. Or one of countless separate universes with their own physics, their own space, their own time. Or both. Or neither, and reality is something stranger still. The common thread is this: whatever produced our universe probably didn't do it just once. The mechanisms that could generate a universe, quantum fluctuations, inflationary expansion, the mathematics of string theory, seem to produce not one universe but many. Possibly infinitely many. We'll break down exactly how each of those mechanisms works. But first, let's talk about why this idea didn't used to be taken seriously, and why that changed. For most of the 20th century, the multiverse was philosophically interesting but scientifically irrelevant. You couldn't test it. You couldn't observe it. By the strict standards of empirical science, it wasn't a real hypothesis, it was speculation. Then a few things happened that changed that status. First, quantum mechanics matured. And as physicists studied it more carefully, they found that one of the most natural interpretations of quantum theory, the one that requires the fewest additional assumptions, implies that parallel realities are real. Not metaphorically, literally. We'll get into this in depth, but the short version is, the math of quantum mechanics doesn't say that particles collapse into one definite state when measured. It says that all possible states continue to exist, and the measurement just determines which branch of reality you end up in. Every outcome happens somewhere. Second, cosmology advanced. Our understanding of the early universe, and specifically of a period of explosive expansion called inflation, produced an unexpected byproduct. The mathematics of inflation almost inevitably generates not one universe but an infinite number of them, all budding off from the same primordial process. Cosmologists didn't set out to find a multiverse. They found one lurking in their equations. Third, string theory, the leading candidate for a unified theory of physics, turned out to have not one solution but something like 10 to the power of 500 solutions. Each solution describes a different universe with different physical laws. Rather than being a problem, some physicists argued this was actually the answer to the fine-tuning problem. Of course, our universe has the constants it has. We live in one of the many universes where those constants allow for our existence. 3 separate areas of physics, quantum mechanics, cosmology, string theory, all pointing in the same direction. That's not nothing. Before we go further, we need to clear something up, because science fiction has done an enormous amount of damage to how people think about the multiverse. In movies and TV shows, parallel universes are usually places you can travel to. There's a portal, a device, a tear in space, and on the other side, there's a version of Earth where the Nazis won, or where everyone is evil, or where you made different choices and everything turned out better. You can interact with your alternate self. You can bring things back. The universes are separated by a barrier that can be crossed. That is not what the scientific multiverse theories propose at all. In most serious multiverse models, the other universes are not somewhere you can go. They are either beyond the cosmic horizon, separated from us by distances so vast that no signal could ever reach them, or they exist in a different branch of quantum reality that has no physical connection to ours. There are no portals, no interdimensional travel, no evil twins. What the science does propose is in many ways more profound and more disturbing than the fictional version. Because the other universes aren't exotic alien realities you visit. They are continuations of your own experience, versions of this world, this life, this moment, that branched off when a quantum event went one way instead of another. They're not over there. In a sense, they're right here, just inaccessible. With that cleared up, let's get into the actual physics. This is the most conservative multiverse, the one that requires the least exotic physics. And yet it might be the most mind-bending of all, precisely because it follows almost inevitably from things we already know to be true. Here's the setup. The universe is about 13.8 billion years old. Light travels at a finite speed. That means the farthest thing we can ever see is something whose light has been traveling toward us for 13.8 billion years. Everything beyond that distance is permanently outside our observable horizon. Not because it doesn't exist, but because its light hasn't reached us yet, and the expansion of the universe means it never will. Now, what's out there beyond that horizon? If the universe is infinite, which many cosmologists believe, then the answer is more of the same. More space, more matter, more galaxies, more planets, more stars. And crucially, if the universe is infinite and matter is distributed through it in a finite number of possible configurations, then every possible configuration of matter must repeat. Somewhere, out beyond our cosmic horizon, there is a region of space that is arranged in exactly the same way as ours. Same galaxies, same solar system, same Earth, same you reading the same words at the same moment. This is not science fiction. This is combinatorics applied to infinity. If you have infinite arrangements of a finite number of types of particles, every arrangement must repeat. Not once, but infinitely many times. How far away is your nearest copy? The calculation has actually been done. Assuming the universe is infinite and random at large scales, your nearest exact duplicate is approximately 10 to the power of 10 to the power of 128 meters away. A number so large it makes the observable universe look like a single atom. But distance doesn't determine existence. If the physics is right, that copy of you is just as real as you are. Living the same life, having the same thoughts, right now. This is the one that tends to hit people hardest. Because it's not about distant copies in an infinite space. It's about you, right now. Every choice you make. The quantum multiverse, also called the many worlds interpretation, emerges directly from the equations of quantum mechanics. And to understand it, we need to revisit something we touched on in our simulation theory video. The double-slit experiment. We know that quantum particles exist in superpositions, simultaneous combinations of multiple possible states. An electron doesn't have a definite position until it's measured. Before measurement, it is, in a very real sense, in multiple places at once. The conventional interpretation of quantum mechanics says that when you measure the electron, the superposition collapses. All the other possibilities disappear. One outcome becomes real and the rest vanish. But physicist Hugh Everett III in 1957 asked a deeply uncomfortable question. Where exactly does that collapse happen? What causes it? The Schrödinger equation, the fundamental equation of quantum mechanics, describes smooth, continuous evolution of quantum states. It never produces a collapse. So why do we observe one? Everett's answer was radical. We don't. The collapse doesn't happen. What happens instead is that the observer, you, the measuring device, everything becomes entangled with the quantum system. You split. The universe splits. Both outcomes happen, but in separate, non-communicating branches of reality. In this interpretation, every quantum event, every radioactive decay, every photon interaction, every electron spin, generates a branching. And because quantum events underlie everything, including the chemistry of your brain and the firing of your neurons, every decision you make is ultimately rooted in quantum processes. Which means every decision creates a branch. Every choice splits the universe. Right now, in another branch, you decided not to watch this video. In another, you're watching it but you paused here and never came back. In another, you're sharing it with someone who will change their life because of it. All of those versions of you are equally real. None is more you than any other. Let's go deeper into Everett's world, because it's more radical than it first appears. In the many worlds interpretation, the wave function, the mathematical description of all possible quantum states, never collapses. It just keeps evolving, branching, expanding. The universe as a whole is described by a single, universal wave function that contains all possible histories of all possible outcomes. This means the universe is vastly, almost incomprehensibly larger than it appears. Our branch, the one where we observe the outcomes we observe, is one tiny thread in an infinite tapestry. Every physical event that could have gone differently did go differently in some other branch. The branches don't interact with each other. Once they split, they evolve independently. You can never communicate with your other branch counterpart. You can never observe what happened in their timeline. From your perspective, the split never happened, you just see one outcome because you are in one branch. But here's what makes this interpretation compelling to so many physicists. It requires no additional assumptions beyond the Schrödinger equation itself. You don't have to add a mysterious collapse mechanism. You don't have to invoke an observer. You just take the math at face value and this is what you get. The price you pay is reality. An infinite multiplication of worlds, all equally real, all equally valid, branching forever. Some physicists consider that price too high. Others think it's the most elegant theory in all of physics. The debate is still very much alive. And now we reach the most extreme version of the multiverse, the one proposed by MIT physicist Max Tegmark, which he calls the mathematical universe hypothesis. Tegmark starts from a simple observation. Our universe is described by mathematics with extraordinary precision. The laws of physics are mathematical laws. The constants of nature are numbers. The structure of spacetime is geometry. Why is the universe so mathematical? His answer, because the universe is mathematics. Not described by mathematics, it literally is a mathematical structure. And if that's true, then there's no reason to privilege our particular mathematical structure over any other. Any mathematical structure that is self-consistent corresponds to a real, existing universe. All of them, every possible consistent set of equations, every possible geometry, every possible set of physical laws. All of those mathematical structures exist, not as abstractions in someone's mind, but as physical realities with beings in them who experience them as their universe. In Tegmark's Level 4 multiverse, there are universes with different numbers of spatial dimensions. Universes where the laws of logic work differently. Universes that are nothing like ours in any way we could imagine. And within all of them, somewhere, are beings who look up at their sky and wonder if they're alone. It's either the most profound idea in cosmology or the most untestable speculation ever dressed up in mathematical language. Possibly both. We talked about the double-slit experiment before, but in the context of the multiverse, it takes on a new dimension, literally. Recall the setup. Electrons fired at a barrier with two slits produce an interference pattern, as if each electron went through both slits simultaneously and interfered with itself. The moment you try to detect which slit the electron goes through, the interference pattern disappears. In the conventional interpretation, this means the electron was in a superposition, and the measurement collapsed it into one definite state. In the many worlds interpretation, something different happened. The electron did go through both slits. Both possibilities were real, but when you measured it, you became entangled with the electron. In one branch of reality, you detected the electron going through the left slit. In another, you detected it going through the right slit. Both U+ electron systems evolved forward in time, each experiencing a definite outcome. The interference pattern disappeared in each branch, not because the superposition collapsed, but because the branches are now separate and don't interfere with each other anymore. The experiment doesn't tell you which interpretation is correct. Both make identical predictions for what you'll observe. That's actually part of the problem, and the reason the debate has lasted for nearly 70 years. But many worlds has a distinct philosophical advantage. It takes the mathematics completely seriously, without adding anything extra. And the mathematics says, all of this happened. Schrödinger's cat is one of the most famous thought experiments in the history of science, and it's almost always misunderstood. Here's the setup. A cat is placed in a sealed box with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector triggers a mechanism that breaks the vial and kills the cat. If the atom doesn't decay, the cat lives. The decay is a quantum event, governed by probability with no definite outcome until it's measured. According to quantum mechanics, before you open the box, the atom is in a superposition of decayed and not decayed. Which means, if you take the math seriously, the cat is in a superposition of alive and dead. Both states simultaneously. Schrödinger designed this thought experiment to show how absurd the Copenhagen interpretation was. Surely, he argued, the cat is either alive or dead, not both. The idea of a macroscopic object in superposition is ridiculous. The Copenhagen interpretation responds, the superposition is real at the quantum level, but by the time it reaches the scale of cats and people, something causes a definite outcome. Exactly what causes it remains unclear. The many worlds interpretation responds differently. The cat is in superposition. Both states are real. When you open the box, you become entangled with the system. In one branch, you see a live cat. In another, you see a dead one. Both are real. Both are you. The absurdity Schrödinger pointed to isn't a problem. It's the answer. Of course, in practice, we never perceive superpositions of macroscopic objects. We always see one definite outcome. Many worlds explains this through a process called decoherence, the rapid entanglement of quantum systems with their environment, which causes branches to become effectively independent and unobservable to each other. The math of decoherence is well understood and experimentally verified. It's one of the strongest arguments in favor of taking many worlds seriously. There's another quantum phenomenon that deserves attention in this context: quantum tunneling. In classical physics, if a particle doesn't have enough energy to get over a barrier, it can't cross it. Simple as that. But in quantum mechanics, particles can pass through barriers they classically shouldn't be able to cross, not by going over but by tunneling through. The particle's wave function extends into the barrier and emerges on the other side. This is not theoretical. This is how the sun works. Nuclear fusion in the sun's core happens because protons tunnel through the electrostatic barrier that would classically prevent them from getting close enough to fuse. Without quantum tunneling, the sun wouldn't shine. We wouldn't exist. In the many worlds framework, every tunneling event is a branching. In one branch, the particle tunneled. In another, it didn't. Both branches are real. Every fusion event in the sun is generating new branches of reality, billions of them, every second. Scale that up to the entire universe over 13.8 billion years, and the number of branches becomes something that makes infinity look modest. You are the product of an unimaginable cascade of quantum branchings, each of which was real, each of which continues to exist in its own thread of reality. The version of you watching this video is one specific path through that labyrinth, one thread in a tapestry of incomprehensible complexity. Let's make this personal. Think about a decision you've made that changed your life. A relationship you chose to be in or chose to leave. A city you moved to or didn't. Career path you took. A moment where you said something that couldn't be unsaid. In the many worlds interpretation, that decision, whatever it was ultimately rooted in physical processes in your brain. Neurons firing, chemicals diffusing, electrical signals propagating. And those physical processes are built on quantum foundations, which means that at the moment of decision, the quantum state of your brain encompassed both possibilities. Both outcomes were part of the universal wave function. When you decided, both branches became real. In this one, you made the choice you made. In another, you made the other choice. And that other version of you went on to live a different life. Fully real, fully conscious, fully experiencing their timeline, just as you are experiencing yours. They don't know about you. You don't know about them. You can't communicate. You can't compare notes. But you share a common past up to that branching point, and from there you diverged. This is not a comforting idea. It means that every regret you have, every road not taken, every mistake, every missed opportunity, exists as a reality somewhere. A version of you is living the life you chose not to live. And a version of you made every error you managed to avoid, and is living with the consequences. It also means that every triumph you've had, every moment of luck, every right choice is equally real in reverse. Somewhere, the version of you that didn't get that break, didn't make that connection, didn't survive that moment is also real. All of those versions of you are equally you. There's no original. There's no copy. The branching doesn't privilege any one thread. Scale that up from individual decisions to historical ones. Every pivotal moment in human history, every battle, every assassination, every invention, every discovery was a physical event. And physical events are built on quantum processes, which means every historical turning point was a branching. In some branches of reality, the assassination attempt failed and the war didn't start. In others, the discovery was made a century earlier or later. In others, the civilization that developed the critical technology collapsed before it could share it with the world. There are branches where Rome never fell. Branches where the Industrial Revolution happened in China instead of England. Branches where the nuclear bomb was never developed. Branches where it was used on a larger scale. Branches where contact between civilizations went differently, with consequences that ripple forward into a present we cannot imagine. And in all of those branches, there are people, living their lives, loving their families, looking up at their sky and wondering about the nature of reality. They are as real as we are. Their history is as valid as ours. There is no main timeline. The version of history we know, the specific thread that led to this moment, this video, this conversation, is one path through an unimaginable space of possibilities. We are not the lucky ones. We are not the chosen timeline. We are one of an infinite number of threads, each as real and significant as any other. Now let's go even further. The multiverse theories we've discussed so far involve universes with the same physical laws as ours, the same constants, the same forces, just different quantum outcomes or different spatial locations. But some multiverse theories predict universes with fundamentally different physics. In the eternal inflation model, when regions of space stop inflating and become separate bubble universes, each bubble can crystallize with different values of the fundamental constants. Different strength of gravity, different mass of the electron, different speed of light, different cosmological constant. Most of these universes would be dead, hostile to complexity. A universe with slightly stronger gravity might collapse back on itself in seconds. A universe with slightly weaker electromagnetism might never form stable atoms. The vast majority of universes that could exist probably contain nothing. No stars, no chemistry, no life, no observers. But in an infinite multiverse, even the tiny fraction of universes that are compatible with complexity would number in the infinite. And within those universes, the beings that evolve would look up at their sky and find exactly the physics they need, and wonder why the universe seems calibrated for their existence. Just as we do. The multiverse is the most powerful answer to the fine-tuning problem. We don't need to explain why our universe has the constants it has. We just need to accept that the vast space of possible universes is populated, and we, inevitably, find ourselves in one that works. To understand where all these universes come from, we need to talk about inflation. In the very early universe, fractions of a second after the Big Bang, space underwent a period of extraordinarily rapid expansion. In an almost inconceivably short time, the observable universe expanded from something smaller than a proton to something roughly the size of a grapefruit. This period is called cosmic inflation, and it was proposed in 1980 by physicist Alan Guth. Inflation solved several major problems in cosmology. It explained why the universe is so flat, why it's so uniform in temperature, why we don't see certain exotic particles that should have been produced in the Big Bang. The evidence for inflation is strong. But inflation has a feature that Guth and others initially found uncomfortable. Once it starts, it's very hard to stop. The quantum processes that drive inflation don't all switch off at the same time everywhere. In most regions, inflation continues. Only in isolated pockets does it end, and those pockets become what we call universes, including ours. This is eternal inflation. Space as a whole keeps expanding, forever. New bubble universes constantly nucleate within it. Pocket universes, each one a Big Bang, each one potentially developing its own physics, its own galaxies, its own life. Our universe is one bubble among an infinite foam of bubbles, each expanding and evolving in isolation. The bubbles can never communicate. They're separated by eternally inflating space. We will never see another bubble. We will never detect one directly. But if eternal inflation is correct, and most inflationary models predict it, then the multiverse is not just possible. It's mandatory. Imagine the multiverse as an infinite ocean. Our universe is a bubble in that ocean, a region where inflation ended and space settled into the relatively stable, slowly expanding cosmos we inhabit. The ocean itself, the eternally inflating background, continues to expand at a rate far faster than light, ensuring that bubbles, once separated, can never reconnect. Each bubble has its own beginning, its own Big Bang moment when inflation ended and the energy of the inflating field converted into the particles and radiation that eventually became matter. Each bubble has its own age. Some are much younger than ours, still in their infancy, stars just beginning to form. Some are much older, their stars long dead, their galaxies dark. And each bubble might have its own laws. The exact vacuum state that the universe settles into when inflation ends determines the physics. String theory predicts an enormous number of possible vacuum states, the landscape of string theory. Each state corresponds to a different set of physical constants. Which vacuum state a bubble universe lands in is determined by quantum chance. So the cosmic foam is filled with an unimaginable diversity of universes. Some have 2 large spatial dimensions instead of 3. Some have no stable matter at all. Some are filled with a single type of particle that interacts with nothing else. Some are close enough to ours that stars form and burn, and on rare rocky planets, chemistry happens, and eventually something looks up. We are in one of those last ones. Looking up. This is the question that most people assume has no answer. But in the multiverse framework, it actually does, sort of. Before our Big Bang, in the eternal inflation picture, there was the inflating background, the primordial space from which our bubble nucleated. That inflating background had no beginning in the conventional sense. It's not that something came from nothing. It's that the conditions for bubble nucleation existed, and our universe is one of the results. But what about before the inflating background? This is where things get genuinely difficult. Some models suggest that eternal inflation itself had a beginning, that there was a quantum fluctuation from a true vacuum state that set the whole thing going. Others suggest that the multiverse is eternal in both directions, no beginning, no end. And then there's a more radical possibility. The question what came before might not be meaningful. Time in our universe is a dimension of spacetime, and spacetime emerged at the Big Bang. Before the Big Bang, before might not exist as a concept. Asking what came before the Big Bang might be like asking what's south of the South Pole. Stephen Hawking made exactly this argument with his no-boundary proposal. The idea that the universe has no boundary in time any more than Earth has a boundary in space. You can travel in any direction on Earth and never fall off the edge. Similarly, you can trace backward in time through the universe and never reach a first moment, because time itself curves away. In the multiverse context, this becomes even more mind-bending. There may be no ultimate beginning, no first cause, No moment before which there was nothing. Just an eternal, self-generating foam of realities, each complete in itself, none requiring an origin. Now let's talk about actual evidence. Because as compelling as the theoretical arguments are, science lives and dies by what we can observe. The cosmic microwave background, the CMB, is the afterglow of the Big Bang. It's radiation left over from when the universe was about 380,000 years old, when it cooled enough for atoms to form and light to travel freely. It fills the entire sky with a nearly uniform glow of microwave radiation, with tiny fluctuations in temperature that seed the formation of galaxies. In 2004, astronomers discovered something unusual in the CMB, a region in the southern sky that is significantly colder than its surroundings. It's called the cold spot, and it is genuinely anomalous. It's about 70 microkelvins colder than the surrounding CMB, and it spans about 5 degrees of the sky, roughly 10 times the diameter of the full moon. Conventional explanations exist. The cold spot might be a statistical fluctuation, unlikely, but possible. It might be caused by a supervoid, a vast, unusually empty region of space that drains energy from CMB photons as they pass through. But one of the most intriguing explanations is a collision with another bubble universe. If our universe and a neighboring bubble collided in the distant past, even a gentle grazing collision, it could leave an imprint on the CMB, a circular bruise, an unusually cold region. The cold spot is exactly what you'd expect such a collision to look like. Astronomers have looked for supervoids that could explain it conventionally and found some candidates, but they don't fully account for the anomaly. The bubble collision hypothesis hasn't been ruled out. This is not proof of the multiverse, not even close, but it is a real, observed anomaly that the multiverse theory can explain and that conventional cosmology struggles with. That's exactly the kind of thing science takes seriously. We've mentioned fine-tuning several times, but let's sit with it properly, because it's one of the most powerful arguments for the multiverse. Our universe's physical constants, the strength of the 4 fundamental forces, the masses of elementary particles, the cosmological constant, are not predicted by any current theory. They're measured by experiment. And when you look at what happens if you change them, even slightly, the results are catastrophic for complexity. Change the cosmological constant by 1 part in 10 to the power of 120 and the universe either collapses immediately or expands too fast for matter to clump. Change the ratio of the electromagnetic force to gravity by a few percent and stars can't exist. Change the mass of the up quark and protons can't form stable nuclei. The universe seems to be calibrated with absurd precision for the existence of complexity and life. Why? Option 1. It's a coincidence. The universe just happens to have these values, and we're here to notice it because we couldn't exist otherwise. The anthropic principle, we observe the universe to be compatible with our existence because if it weren't, we wouldn't be here to observe it. Option 2. There's a reason. Some deeper theory we haven't discovered yet will explain why the constants have to be exactly these values. They're not free parameters, they're determined. Option 3. The multiverse. The constants vary across universes, and we live in one of the rare ones where they happen to be compatible with life. No calibration required, just selection. The landscape of string theory, with its 10 to the 500 vacuum states, provides exactly the diversity of constants you'd need for this to work. Many physicists find option 3 deeply uncomfortable, because it seems to remove the possibility of ever explaining why our constants are what they are. In a multiverse, why has no answer beyond because in this one they are and in most others they aren't. Others find it the most honest answer available, given what we know. The Large Hadron Collider at CERN is the most powerful particle accelerator ever built. And while it has scored major triumphs, including the discovery of the Higgs boson in 2012, it has also produced a result that some physicists find unsettling in its implications for the multiverse. Specifically, the LHC has found nothing beyond the standard model. No supersymmetric particles. No extra dimensions manifesting at accessible energies. No exotic new physics at the scales it probes. Why is this relevant to the multiverse? Because the most popular extensions of the standard model, the theories that were supposed to explain the hierarchy problem and other unsolved puzzles, predicted that new particles should be visible at LHC energies. They weren't there. This absence is, for some, indirect evidence of the multiverse. If supersymmetric particles don't appear where theory predicted, one explanation is that the hierarchy problem doesn't need solving by new physics. Instead, the value of the Higgs mass is what it is because we live in a universe selected from a multiverse landscape, and in our patch, the Higgs mass happens to be compatible with the chemistry of life. No naturalness required. This is known as the nightmare scenario for particle physics, because it suggests that there may be no new physics accessible to any accelerator we could ever build. The explanation for why our universe is the way it is might be entirely environmental. We're in a universe where it's this way, among many where it isn't. Not everyone accepts this reasoning. Many physicists think the absence of new physics just means we need a better theory, not a multiverse. The debate is ongoing. Here's the central problem. By definition, other universes are beyond our observational reach. We can't send a probe there. We can't receive a signal from there. The very structure of the theories predicts their inaccessibility. So how would you test any of this? The bubble collision idea offers one possibility. As we discussed, a collision between our universe and a neighboring bubble should leave a distinctive circular imprint on the CMB, a specific pattern of temperature variations with properties that distinguish it from other anomalies. More detailed maps of the CMB from future telescopes and satellites might find such patterns, or definitively rule them out. The decoherent structure of many worlds offers another potential avenue. Some physicists have argued that the Born rule, the formula that gives probabilities in quantum mechanics, can be derived from the structure of the many worlds branching, rather than being an additional axiom. If we could verify this derivation experimentally, it would be strong indirect evidence for the many worlds picture. Gravitational wave astronomy opens another window. The very early universe, the inflationary epoch, should have generated a background of gravitational waves with specific statistical properties. Future gravitational wave detectors might measure this background. The specific pattern of those waves could help distinguish between inflationary models, some of which predict eternal inflation and a multiverse, and some of which don't. None of these is a direct detection of another universe. But science rarely works by direct detection of its biggest ideas. We didn't directly observe atoms for decades after the theory was established. We inferred black holes from their effects on surrounding matter long before we imaged one. The multiverse might be testable through its signatures, its indirect fingerprints on the universe we can observe. There's a more pessimistic view, held by serious physicists, that the multiverse is permanently beyond the reach of science. Not just difficult to test, in principle untestable. The argument goes like this. Science works by falsification. You make a theory, you derive predictions, you test them, and if the predictions fail, you abandon the theory. But the multiverse makes a prediction that is unfalsifiable. It predicts that we should observe a universe compatible with our existence. We do. But we would regardless, because if it weren't, we wouldn't be here. The anthropic principle makes any observation compatible with the theory. Moreover, the specific predictions of string theory's landscape, what our constants should be in a multiverse, are not precise enough to be testable. The landscape has 10 to the 500 vacua. With that many options, you can explain almost any set of constants as likely or typical. A theory that can explain anything actually explains nothing. Critics like philosopher Jim Baggett have called the multiverse fairy tale physics, not because the idea is crazy, but because it has abandoned the commitment to testability that defines science. If a theory can never be tested, is it science? Or is it philosophy dressed in mathematical clothing? This is not a dismissible concern. The history of science is full of theories that seemed compelling and even beautiful but turned out to be wrong. The multiverse might be the most elaborate, mathematically sophisticated, physically motivated wrong idea in the history of human thought. Or it might be right, and we might never know for certain. The multiverse debate is really a debate about the boundaries of science itself. Traditionally, a scientific theory must make testable, falsifiable predictions. The multiverse, in most of its forms, doesn't, at least not directly. Does that disqualify it? Some physicists say yes. Science is about what we can know through observation and experiment. A theory that requires entities beyond all possible observation is metaphysics. not physics. No matter how elegant the mathematics, if you can't test it, it's not science. Others push back. Theoretical physics has always extended beyond immediate observability. When Einstein proposed general relativity, there was no technology to test some of its predictions. When Dirac predicted antimatter, it hadn't been detected. We extended science's reach by developing new tools. Maybe the same will happen with the multiverse. And there's a third position increasingly common. The question of whether the multiverse is science might be less important than whether it's true. If the mathematics of inflation and quantum mechanics genuinely implies the multiverse, if it follows inevitably from our best theories, then the multiverse exists whether we call it science or not. The universe doesn't care about our epistemological categories. What we can say is this: the multiverse is a serious idea, taken seriously by serious people with real mathematical foundations. It might be testable. It might not. It might be true. It might not. And the honest answer for now is that we don't know. And the uncertainty itself tells us something profound about how far we still have to go. If every decision you make creates a branching, if every possible outcome of every choice you face actually happens in some branch of reality, then what does it mean to choose? The question is genuinely difficult, and people's intuitions split sharply on it. One reaction is nihilistic. If everything happens anyway, nothing matters. Whether you work hard or give up, whether you treat people well or badly, whether you pursue your dreams or abandon them, all of those choices are made in some branch by some version of you. So why bother? The outcome you experience is determined by which branch you end up in, and you have no control over that. But this reasoning has a flaw. It confuses the many-worlds structure with fatalism. In a many-worlds framework, what determines which branch you follow is the actual choice you make, the physical process of your decision. You are not a passive observer watching which branch unfolds. You are the branching mechanism. Your choices are what create the branches. Think of it this way: in every branch, some version of you is making a choice. In the branches where that version chose well, they experience the consequences of a good choice. In branches where they chose poorly, they experience the consequences of a poor choice. You, right now, are choosing which branch of your future to inhabit. The fact that other branches also exist doesn't change that. Another way to frame it: meaning doesn't require uniqueness. Your love for someone isn't diminished by the existence of other people who love other people. Your experience of this moment isn't less real because other moments are also real. The multiverse multiplies existence, it doesn't devalue it. This is the most unsettling application of many worlds, and it's important to engage with it carefully, because it leads somewhere genuinely strange. There's an argument, controversial, speculative, but logically derived from many worlds, called quantum immortality. It goes like this: in any situation that could result in your death, there is a quantum branching. In some branches, events unfold in a way that leads to your death. In others, they unfold slightly differently, a 1 in a million coincidence, a quantum fluctuation, something, and you survive. If consciousness only exists in the branches where you're alive, because you can't experience death, only the subjective perspective of surviving, then from your first-person perspective, you will always find yourself in the branch where you survived, no matter how unlikely that survival was. The implication is that from your own subjective point of view, you can never experience death. You will always find yourself in the branch where you made it through. You are, in a very specific sense, quantum immortal. However, and this is crucial, all the other versions of you, the ones in the branches where you didn't survive, are also real. Their families experience their loss. Their absence is real in those branches. Quantum immortality, if it's real, offers no comfort to the people who love you. It only changes the structure of your own first-person experience. Most physicists are deeply skeptical of quantum immortality as a practical matter. The branching doesn't work cleanly enough, decoherence is too complex, and the subjective selection effect is questionable. But as a thought experiment, it illustrates how radically the multiverse changes our concepts of identity, continuity, and mortality. Here's the question that cuts deepest: what is identity in a multiverse? Right now, there are versions of you who made different choices, live different lives, have different memories. Are they you? In what sense? They share your origin. At some point in the past, you were the same person, the same physical system, the same state of the universe. Then a branching happened and you diverged. Since then, each version has accumulated different experiences, different memories, different relationships. You are increasingly unlike each other. If you met a version of yourself who diverged 10 years ago, you would recognize them. But they would be deeply different, shaped by 10 years of different experiences. Like a twin who grew up in different circumstances. Clearly related, clearly not identical. And what about the version of you who diverged 1 second ago? Or 1 millisecond? At what point does the other branch become a different person rather than a continuation of you? The question has no clean answer, because identity itself doesn't have a clean answer, even in a single universe world. We are not static things. We are processes, patterns that persist through time, changing continuously. The you of 10 years ago is not the you of now, not in terms of your atoms, your memories, your beliefs, your personality. The multiverse just makes this fluidity more vivid. It reveals that you was never a fixed, singular thing. It was always a branching, evolving, context-dependent pattern. The multiverse doesn't undermine your identity. It reveals what identity always was. And that, perhaps, is the most profound gift of this whole line of thinking. Not terror, not nihilism, but a new way of seeing what you are. Not a fixed point, but a living process. Not a thing, but a story. And in infinite parallel universes, infinite versions of that story are unfolding right now. Each one complete, each one real, each one irreplaceable within its own thread of existence. We started with a question. What if there are other versions of you, right now, living lives you can barely imagine? We've seen that this isn't a fantasy. It's a conclusion that multiple serious physical theories converge on, from quantum mechanics to cosmic inflation to string theory. The multiverse isn't a single idea, it's a direction that the mathematics of reality keeps pointing toward, from completely different starting points. We've seen the different types of multiverse. The infinite space beyond our cosmic horizon, the quantum branching of many worlds, the bubble universes of eternal inflation, and the full mathematical landscape of all possible physical laws. Each is strange. Each is supported by real physics. Each changes what it means to be here. We've seen the evidence, the anomalies in the CMB, the fine-tuning that demands explanation, the failures of beyond standard model physics that hint at a landscape rather than a unique set of laws. And we've sat with the implications, the fluidity of identity, the strange logic of quantum immortality, the question of whether choices matter when every outcome happens somewhere. Here's what I want to leave you with. The multiverse, if real, does not diminish this universe. It doesn't diminish your life, your choices, your relationships, your moments. If anything, it contextualizes them in the most profound way possible. You are here in this specific thread of reality because of an unimaginable cascade of events, quantum and cosmic, that led to exactly this moment. In countless other branches, that cascade went differently, and you are elsewhere or not yet born or gone. But in this branch, in this universe, you are here, experiencing, thinking, wondering. That is not nothing. That is, perhaps, everything. The universe, this one, yours, is not less remarkable for having company. A single flower is beautiful. A field of flowers is breathtaking. An infinite garden of flowers, each unique, each real, each blooming in its own reality. That's not a diminishment of beauty. That's the most beautiful thing imaginable. And somewhere in another branch, another version of you just heard that for the first time.